I'm mechatronics manager at Quanser, and here today we're demoing a bunch of our products which interface with LabVIEW products. So this here is inverted pendulum, and it is part of the QNet line. These are controls plants, experiments that interface to the LabVIEW's ni-elvis and ni-elvis 2, and they provide physical plants or problems that students in controls courses have to try to solve controls problems for. So in this case here, so we got a nice demo of the inverted pendulum. It's a classic controls problem. And what we have is a DC motor acting on a little link here, and the position of this pendulum is being measured by an optical encoder. So as the optical encoder measures this thing falling off, the motor at the bottom moves in that direction based on some state space control laws to try to catch it. So take a little image here. We've also got another algorithm in which we can swing it up and catch it.
What's this one here?
This here is a DC motor module. This is a very good topic to teach introduction to controls. There's a DC motor with an optical encoder and an inertia, and the students would go through all the typical controls steps of modeling and analysis, and then controller design, and then validation and verification.
Cool. And what about these three boards here, Derry?
So these three boards are three additional experiments. This is a new one we have. It's a QNet myoelectric board. We have a myoelectric sensor which can measure impulses of the muscles.
Awesome.
And we are using those to control a small robot gripper. The challenge on this one is a lot more about signal conditioning and interpretation of these noisy signals. And we have just a nice little output here, so you can have something practical to do once you actually do analyze signals properly. This is a heat flow experiment for fluids or thermodynamic instruction, which we have a fan at one side, a heat source, and some temperature sensors, and we can again model the system and predict what it's going to do and try to control it. Lastly, this is a mechatronics sensor kit. So we have a myriad of different sensors from sonar to optical distance to switches, an optical encoder up here, a couple of other distance sensors. And the main purpose of this is to teach students how to interpret and interface to these different sensors. For example, on these switches, when you close them, you see what they call bouncing. You see it go from close to open to close in a very quick succession. The students would then have a challenge of writing a LabVIEW program in order to interpret that signal as a clean switch. The encoder module up here, you get the classic A and B 90 degrees out of phase signals, and they have to now write a little bit of logic in order to increase and decrease the count.
Cool. What about this guy here?
So here we have the last QNet is a VTOL. It's a vertical takeoff and landing plant simulator. The students are able to control the voltage to the motor in order to provide a thrust, and the position of the arm is measured via this encoder. Something kind of exciting that we're coming up with a prototype right now, then showing it at ni-elvis is my plant, and my plant is a virtual representation of the QNet VTOL.
Okay. Can you show us that?
I can. So, using the exact same control code developed in LabVIEW that we were using to control the real device, we can now command and control the virtual plant.
Very nice.
So the key to this system, it is a high-definition nonlinear model which very truly represents and accurately represents the dynamics of the real system. The nice thing is that real signals, so like analog commands coming from ni's MyDAC, command the position or the speed of the virtual motor, and then real encoder pulses are fed back. So this is a hardware in the loop simulation, which is very important these days. We have a piece of software as the controller, a piece of software as the model, and real interfacing signals back and forth between the two devices. So the uses of this are many, but one could be to allow the students to have a version of the beautiful QNet plant at their house and spend as much time as they want actually doing labs and developing their controllers and getting excited about controls. Then when they come into the lab, they have a real understanding of how the system works, and they can deploy their real controller onto real hardware. This is the way real engineers do controls work.
Awesome. So just to sum up, we've got the DC motor control trainer, we've got the rotary inverted pendulum, the QNet HVAC trainer, the VTOL trainer, mechatronic sensor trainer, and last but not least, the myoelectric trainer, coming out soon.
I'm Sunny, Quanser evangelist. This is the Quanser SRV02. This is probably our best-selling product. We use this to teach position and speed control. Usually with the Volpac X1. In this case here, we've got it set up with a C-Rio, and we've got a LabVIEW VI that's driving this system here. So the SRV02 is actually the base. So like I said, you can teach position and speed control with this system. But then there's 14 different modules that go on top of the system that allow you to teach